47 when we're done. All right, so today we're looking at exponential functions. We've already talked about them again a little bit because we did the geometric sequences. So it starts by saying in math, we study several different types of functions, obviously. 3 types that keep coming up: linear, algebraic, and algebraic, linear, quadratic, and exponential. What does the exponential graph have that the other two do not? What? Asymptote. Yes, very good. Whoever said that? Asymptote. Asymptote right there. I know. I don't even know where I'm looking. All right. Yeah, not an asymptote, but an asymptote. So it has an asymptote, right? So that's one of the obviously a lot of differences here. But exponential functions, they are some of the most important in the real world because they appear in lots of places: population growth, money, which everybody's concerned about, radioactive decay, spread of disease, etc. In addition, the SAT has several questions that require an understanding of exponential functions. Okay, you don't have to be experts, but you got to have some understanding of them. So some key characteristics. We've looked at the general form the other day when we were doing the geometric sequences. So when I have it in this form here, A and B are constants, which just means that they're numbers that'll go in there. A cannot be 0. If A was 0, the whole thing would be 0, so it doesn't make any sense. B cannot be 1, because if B is 1, 1 to any power is still going to be 1, and this function wouldn't be doing anything, right? B can also not be 0, because then the whole thing is 0, and none of it makes any sense. But B does have to be greater than 0. So B itself is not going to be a negative number, right? And just like in the same positions that these variables are in for the geometric sequences, A represents the initial amount, and B represents the common ratio. Right. So then we've talked, well, and I know before you have talked about exponential growth and decay. That is something, one of the applications that you use a lot. Not every exponential function can be classified as growth or decay, but if you're going to talk about them that way, then A is greater than 0 no matter what. Now, if A is negative, we can have a reflection, but then we don't talk about it as growth or decay. It's just a different kind of function. So in both of these, A is greater than 0. If B is greater than 1, then that's your exponential growth. That would have been the first one that you were introduced to. If B is between 0 and 1, so like 1/2, 3/4, then you get your exponential decay, right? For growth, we can say that the function itself, is it increasing or decreasing? The function, increasing. And is the function concave up or down? Up. Good, so in concave up. Now then, if we want to talk about the rate of change, what should we write down? The fun chart. Okay, been a minute since we did all that, but we still need to do that, so need to be able to do it. Write down our fun chart. So then tell me, for exponential growth, is the rate of change increasing or decreasing? Increasing, because the function is concave up, right? So rate of change is increasing, and is the rate of change positive or negative? Positive, because the function is increasing, right? Okay, good. So then for exponential decay, is the function increasing or decreasing? Decreasing, right? And is the function concave up or down? Still up. Still up. Concave up. So then what about the rate of change? Rate of change. Did I just hear somebody scream? Yep. Okay, just making sure. Is the rate of change increasing or decreasing? What is it? It is increasing, because the function is concave up. Increasing, and is it positive or negative? Negative. okay? So in both of these, the rate of change is increasing. So we can talk about this function is increasing at an increasing rate. This function is decreasing at an increasing rate. So whatever's happening is just happening faster, whether it's getting bigger or getting smaller, it's speeding up. Okay? Does that make sense to you? All right. Use that fun chart because it's easy to get that stuff all mixed up in your head and overthink it, but remember the fun chart. And don't mess up your fun chart. All right, so exponential functions are always increasing or always decreasing, right? It's always one or the other, so there are no relative max or mins, no relative extrema. It's always one or the other. Same thing with the concavity. Always concave up or always concave down, so they have no points of inflection. Those just don't exist here. Then if we think about our in behavior, here as x approaches negative infinity, what is the function approaching? Zero, because of that asymptote. As x approaches infinity, what is the function approaching? Infinity, okay? Here, as x approaches negative infinity, what's the function approaching? Infinity. And as x approaches infinity, the function's approaching zero. So your only answers to these limits are infinity, negative infinity, or zero. That's it. Okay, and that's basically what this says here. As the input values increase or decrease without bound, output values will increase or decrease without bound, or will approach zero. So no matter whether I'm approaching positive or negative infinity, my answer is either infinity, negative infinity, or zero. My only options. And that is for, and it says right here, in general form. General form means we're not shifting up or down. We don't have any shifts. Okay, so you shift up or down, it's going to move that asymptote and it would change the zero, but we're just talking general form. Okay, everybody good with all that? Any questions? All right, flip it over. All right, so let's talk limits. I mean, we pretty much just said that. These need names though. So let's call this guy f. So we're going to write the limit. If it's to the left, it's x approaches negative infinity of f of x. So as x approaches negative infinity, what's the function approaching? Zero, because we have an asymptote. And the limit as x approaches infinity of f of x would be infinity. Yes. All right, let's call this next one h. H. And so the limit as x approaches negative infinity of h of x, what's that going to be? Negative infinity. And the limit as x approaches infinity of h of x would be 0. Okay, those make sense to you? All right, so then when you don't have a picture, because when you have a picture, it's usually pretty helpful. But here, the 5 is just the stretch, so that doesn't really change any of the limit stuff here. But that 2/3, since that is between 0 and 1, that is exponential decay. So you need to have that picture in your mind, or at least sketch it down for yourself. And this would be the limit as x approaches negative infinity of g of x. What would that be? Infinity, good. And then the limit as x approaches infinity of g of x, that will equal what? 0. Okay. What questions do you have? Anything? All right, let's talk about what this this equation could look like. If I see that as a reflection of either exponential growth or decay, before it's reflected, it would look like that, right? And then it would reflect in the x-axis. So if it looks like my light pink one there, that would mean whatever's in the parentheses, like 1/2, that would have to be between 0 and 1. I have no idea if it's 1/2 because I have no scale. I'm just giving you an example of whatever. And then the number outside of it, let's say it could be 3. But then if I needed to do that, that 3 would be negative. So that is a possible function or equation that would graph something like what we actually had there. Okay, to think about what's happening with those reflections. We okay with that? No? Too bad. All right. Don't even know why I asked. All right. So this should be a piece of cake right here. For each of the following, determine if the exponential function is increasing or decreasing or concave up or down. Do I need my fun chart?
Not really.
No, because I'm not talking about rate of change, right? If I write down my fun chart every single time I ever do anything, that's when we get confused about when we're supposed to use it. Only if I care about, this has nothing to do with rate of change. Is this function here increasing or decreasing? Decreasing. And is it concave up or down? Up. Okay. I don't know why I asked that backwards, but I did. B, concave up or down? Down. Increasing or decreasing? Decreasing. Good. Then this one, the B part is greater than 1, so it is increasing, right? Because that there's the 3 is not negative. So the function's increasing and it is concave up. Although it doesn't do this like I just did that. How do I know it's concave up? Because, well, for a couple of reasons. Just a second. That's a little better picture there. So up like a cup, down like a frown, right? So even though with the exponentials, they don't actually make a cup like a parabola would because it comes out flat, but this is, you know, it's kind of like a smile and a frown. Does that help? We good with those? Anything else? That's a good question. Okay. Let's look at this here. Selected values of the function f are shown in the table. Determine if f could be linear, quadratic, or exponential. So we added quadratic to what we were looking at yesterday, or none of these. What should we always start by looking at first? The x values, right? The change there, yeah. So I want to look at for my change in x. And that's going to be 5 and 5 and 5 and 5. Okay, so that's what I wanted to happen. I needed to happen so I could actually go forth and figure the rest of the stuff out. Okay, so now when I look at my y values, if I thought about the ratios, like if I put 5/3 and 9/5, are those the same thing? No, so I'm not going to bother writing my ratios. Could be quadratic, so let's go ahead and do our differences. So delta y, 5 minus 3 is 2, 9 minus 5 is 4, 17 minus 9 is 8, and then this is 16. Okay. So right there, is it linear? No, because those numbers are not the same. Now, if I was to do my second differences and they were the same, that would mean quadratic. Well, if I do 4 minus 2 and 8 minus 4, are those going to be the same thing? No, it's not quadratic. But now that I have those pink numbers written there, do you see any other kind of pattern or what it kind of looks like now? Would the ratios work here? They would, right? Look at what happens if I do this ratio. 4/2 is 2. 8/4 is 2. 16/8 is 2. And that's multiplying by 2. So let me put it on there. All right. So instead of just getting the ratios in the first try, we did differences, then there were ratios. What that means is that this is exponential, but there's a translation in there. Okay? And so what we were looking at yesterday was just straight up in general form, no translations. But because I do the differences and then I can see the ratio, that makes it exponential. Okay? So we're going to have to start checking a few other things as we go through. Questions about that? No? We good? Okay.